Hi, is this working? Yes, looks so. So, hi, I hope you enjoyed the very long break. I am Agata Trovato. I come from Trieste in Italy, and I am very deeply involved with the Gravitational Wave Open Science Center. So I will discuss about our open data. So first, I want to give a brief introduction about open science in general. So the idea that the science should be open is recent, relatively recent, but it's quite important to allow the research to be reproducible and so also accessible and transparent. The fact that we publish so we make public our data, the code that we use, we explain how we get the results we obtain. It's really important to allow everything to be reused and in this way also to increase the impact on what we do. And this some also faster the scientific progress, because if all the people in the community interact among them and they exploit what each other, what they do, this really improves our scientific project. And the reproducibility also increases the trust in our result. So, and in general, when you hear about open science, there are the principles called FAIR principle, where FAIR is an acronym of findable, accessible, interoperable, and reusable. So this is just to introduce what on the concept of open science. And in this sector, the LIGO Virgo Kyocera collaboration is really active, because we publish our data, we share the tool that we use, the Python packages you will use in all the tutorials. Most of them have been written by members of the collaboration, but then they have been made public. And then we also engage the community, and this workshop is part of this engagement, because we explain people what we do, how we do it. So the open science principle are in the case of the LVK collaboration, the main center for open science is the Gravitational Wave Open Science Center. That is a website that is reachable at the URL that you see at the top of the slide. And this is a screenshot of the web page. And you see there are many buttons. I will come back to some of them. But you see already from the button that there are focus on the data, on the catalog, so on the events we detect, but also on the tutorial, on the workshops. So on we put our time and effort both to publish the data and to allow users to understand our data. And in general, when some scientists use our data in one of her publication, we ask to acknowledge our papers, because we have in this page that you see here, there is a list of papers. They are quite small here, but I don't want you to read the title. They are papers about the open data that we have been released. And just tracking the citation to this paper, we realize that the interest in our data have really increased with time. Here you see a table. In the x-axis, there are the year. Starting, the first column is 2015, so the first discovery, and the last column is last year. And I counted the number of citations of this paper using as source Inspire. And as you can see, the number of citations nicely increased with the year. And now in the recent years, we have had more or less 200 citations per year, which means that there are 200 papers at least that use our data. There could be others that I forgot to cite. So this is the minimum level of papers that use our data. So just to explain, to highlight how releasing our data increase the impact of our science. Then before going to the content of the, in terms of data of the website, I want to highlight that there are various ways in which we engage with the community. On the, you see here the list of workshops. You are in the 9th of workshops. We have done one each year. So the Gravitational Wave Open Science Center group every year organize a tutorial or help organizing it. But then in the website we have resources for also younger students. So this learning path is a more gentle introduction to gravitational wave data. And then there are very different kinds of tutorials, not only the one that you see in this workshop. And then, as Matthew mentioned, we use a lot recently this website, ask.egwin.org, is as a forum, so to collect questions. Our hope was that it would become like the Stack Overflow for questions concerning gravitational wave data, and we do our best to reply to the questions that are there. Okay, so now let's go to the data products that you find online. So the main data product is the calibrated strain, as Viola was mentioning, and you see an example. This is one of the plots that you will produce in the tutorials. So this is just the strain over time. And not only we, of course, the strain is associated with a lot of information. We give the uncertainties and the bias, as Viola was mentioning, but also all the information about data quality, if there were injection, a lot of documentation. Then another important concept and another important source of information that we have in our website are the segments. I will come to that, I think, in my last slides, but you can see already from this screenshot that in the segments are really segments, so start and stop with the duration, and this is really important because the detectors are not active always. So if you need to download long stretches of data, you have to know which start and stop the data exist. And then we have a lot of analysis result. What you see in this slide, these are, I think these are posterior sample, and this is a sky map. These have to do with the CBC. So the result Viola was mentioning, the result of the search of compact binary coalescence. And actually, the plot that you see here, these are on Zenodo. But what we have in the GWOSC website, besides the strain data, the segments are all the information about the catalogs and events. And I will come back to this later. So let's start with the data releases. The first concept to understand when trying to use our data is that the data releases are divided into, can be divided into groups, let's say. We release the whole data that we have collected after the end of each observing round, not directly after the end, but we need a period of proprietary period so that we can check. We check the calibration, we analyze the data, and after that we release that. But if there is a detection associated with the paper, we release directly the data after the paper is published. And in this table, I collect a couple, the list of the times in which the observing run data were published, just to give you an idea of how we work. So, okay, the first line is just to remind that special events and catalogs are the date of release is the publication of the paper. But then, for example, O1 was published more or less 2 years after the end, and a bit less than 2 years for O2, and then with the time that passed between the end of the observing period and the date of release is reducing more and more. So we are doing an effort to give the data to the users as soon as possible. Now we have just ended our 4th observing run, and the first block that in jargon we call it O4A was released in last August. But now we are working on the data release of O4B, so the second block, that will be released at the end of May, so next month. So this will be the next big data release. So let's see how you. Let's assume you want to get our data through the website. How will you do that? Here in these slides, I used as background the screenshot of the website I was showing at the beginning of the talk. And if you click here on Get Data, you get this menu. And the first link datasets bring you to this page, which you see the list of all the observing run. And each, you have a long page now, because we have many releases. And this is a screenshot of the last thing that was added to that page. So this is the O4A data release. And then, as you see in this screenshot, these orange things here, they are buttons that you can click. I will show in a moment what you get when you click on 4 kilohertz or 16 kilohertz is the same. But then you see associated to each run, you have a lot of documentation. Then you have the timeline, that is the thing related to the segments I was mentioning earlier, and I will come back to this later. And then you have additional buttons like this, because in some case we release also auxiliary data, so data that comes from auxiliary channels, so not only the strain, but other witness channels. This is released only for LIGO. And then we release also what is called the alternate strain. We started by releasing the name alternate strain come from the fact that we wanted to release alternative version of the calibration, because sometimes we have different calibration version, but then recently we are start to use this to release the data as they are. So this is an additional kind of release that I will not come back to later. But you can also, it's available also on the website. So instead, if you click on this button, 4 kilohertz, 8 kilohertz, you will arrive to a page like this. You see a table. Basically, you have many lines. Each line corresponds basically to one file. So the first column that says timeline is the link to the segments, and you see you see a number with 10 digits. This is the GPS time. I put here the definition in case you are not familiar, but it's the time, the second elapsed between one reference time, and it's always 10 digits for us. Then you see how big is the file in megabytes, and then you see you have two links for the two formats that we released, HDF5 and Frame. Frame is a proprietary format that we developed. And then the last number tells you for how much of the time this the data were on. So because each line refers to 4,000 seconds. So this says that in this 4,096 seconds, to be precise, for the 20, you have the 22% of data. So if you click to one of these, for example, HDF5, you get one of these files that has this weird long name, but if you look at it, it has a structure. So the first part refers to the detector, then Vygotsky is to say that is, yes? Okay. And yeah, the WASC is the because we repackage the data, then the run of array in this case, and then the sampling frequency, and then the GPS time of the starting of the file and the duration. So when you download the file from this page, it has this weird name. And what is inside each file? This is a structure. Okay. So basically, this would be 100 for each file. The percentage tells you. So if it's 100%, in which it means in this period of 4,096 seconds, you will have time always. This 22%, it means that you have time only in the 22% of these 4,000 seconds. Okay. So I was saying the content of each file can be seen easily. This is an HDF view, a program that shows the content of the HDF5 files. And as you can see, there are 3 folders. One that is called that has to do with the metadata. So all the information of the file, the GPS time, the instrument, and so on. Then we have another folder that is called quality, and that contain basically 1 hertz time series. So a time series that is sampled for each second of data, and refers basically to the data quality in that second. Basically tells you the data quality category to which the data belongs. And finally, the strain, which is the main information. So as I was saying, this HDF5 we provide to the users because it's more flexible, but then the internal format we use is what is called frame format. And in the past events that were published, you will see also in some case a TXT format. So what I said, it's the way in which you get the data if you browse the website, but you will use in the tutorial Python code. And the way to get the data with the Python code is using the easiest way is using one of the 2 Python packages, GWPy or PyCBC. You will see that in the tutorials of that we will play with tomorrow morning. And these are taken as screenshots from the tutorial about the data access. And you can see that in a couple of lines of code, you can get a piece of data. You will play a lot with this. And I have to warn you that GWPy is in general faster to get the data than PyCBC. It's a bit more optimized for this job, but you can play with both. Okay, then I talked about the observing run, but I was mentioning that we provide also analysis information about the analysis, and the main information is related to the event that are in the gravitational wave transient catalogs. You will hear more about that probably in the talks about specific about CBC, but just to warn you, because you will see this acronym already in the tutorials you will play with tomorrow. So GWTC is the way the acronym used for the gravitational wave transient catalogs, and each of them is a collection of transient signal that we have discovered in the data, and these signals are basically merger of compact objects, so black holes or neutron star. This plot show starting, so in the x-axis you see the year, the colored band refer to the various observing periods, and here in the upper part the ticks show you the different catalogs. And if you want to have a look at the different catalog, this underlined text is actually all these yellow underlined text are all links to the specific catalogs. And another in our page we have I think a structure, what is called the event portal that you can get from this page. And all these boxes are buttons that you can click depending what you want to get. So the upper button brings you to a list of all the confident detection. Then you can query for the releases or for the single events or for the query form. And in terms of the various release that we have, you will see a page like this. This I cut it because it's a very long. Page. As you see, in many cases, the release name starts with GWTC, so the catalog, and in some cases you have at the end something like confident marginal, because for some candidates, for some catalogs, we have released both marginal and confident detection. Then I didn't put the screenshot of everything, but if you scroll down, you will see something that has discovery papers in the name, and this is where we collect all the papers that are published before catalog. And then you will find also one catalog that is actually not an LVK catalog, because recently we are starting also to host external catalogs. Okay, then another way to search for event is the query form, which is, this is a screenshot of how it looks like. So you can query events by name, type, time, release, by interval of the by parameters. And finally, when you get to one of the list of events, when you click to one release, one catalog, whatever, you will end up to a page that looks like this, that has the list of all events, and that if you click on the right side on display, you can choose which parameter you want to see on this page. Then if you in one of these lists, you click in one of the events, you will arrive to a page like this that is specific for an event. And as you can see, you have, this is quite small, so you cannot see, but everything that is yellowish is a link. So you have a lot of documentation, a lot of information on the event. Then you have the QScan that show you visually how the data for that event look for each detector that was active. And then you have some links to detect, to download data around the event. And recently we have also added this interactive plotting that allows you to print some detail of the P when is available. So I've shown you again in terms of the events of the catalogs, how to browse the website, was what you can find it. But again, most of these things can be done by Python code. And also in this case, the Python package that interact with the website is called Gwosk. And you will play with it in the first tutorial, actually, because it's very easy to use. and you will learn how to do many things, how to find dataset, events, catalog, how to check which is the GPS time of an observer run, which is the URL if I want to download a dataset, how to get a list of events filtered by parameters, which is basically what the query form I was showing you earlier does. But be aware that what you will do by playing with it is probably done also behind the scene by the packages that you use also the other days, because this WASC packages is used a lot by, for example, GWPy to query for the data and to find all these properties of the data. Okay. So I'm almost done. I want to stress one thing. You will not play with this a lot during the workshop, because you will always be given a short period of time for which downloading the data. But be aware that if you work with longer periods of time, on the you have to be always careful when you download the data, because as I was saying, the detectors are not always in science mode. As Viola was explaining, keep the detector in lock, so in the equilibrium condition is not easy. So that is why you have to be aware that if the detector is on, at some point you will have start and stop of data taking, actually. But besides that, it could be that in addition to the start and stop of the lock, you want that your data meet the basic requirements. So you can have some filters on your data. So you have the conclusion is basically that the analysis is always applied to data segments. So you have to have a way to find which is the start and stop that you really need to use. And the easiest way to get this start and stop is via this timeline tool. And if also this is a link, so if you click it, you will see a page that allows you to decide if you want to download the segments for one or multiple detector, and you can specify also some data quality categories you may want to have, and I think Francesco will show about this. We will mention this data quality a bit better tomorrow. And what you see in the bottom is a screenshot of an example of L1 and H1 data. I think this is O4A, if I'm not mistaken. Yes, this is O4A. And the colors show when the data were on. So for example, you can see that there was a hole, apparently a hole here. Actually, this is not a hole. This is because we released also a piece of data in the engineering run before the starting of O4A. And then at the end, there are other holes here in the data. So you have to be careful about that. Okay. And I think that's all, yes. So I hope I convinced you that the Open Science, the Gravitational Wave Open Science website is a successful project. We have a large community of users, many publications related to the gravitational wave astronomy cite our papers, so I've used our data. I put here a screenshot of a couple of years ago in which the CERN Courier was advertising that LIGO and Virgo published their data only a few days after the announcement of the first observation of gravitational waves, just to say that also what we do went also in the CERN radar. As I was saying, we have recently publish the O4A data, we will publish O4B data and catalogs associated with it at the end of May next month. And at the end of the year, in December, we will publish O4C. So stay tuned. There will be a lot of science to come. Thank you.
Thank you, Agatha. This was a very interesting talk. Before taking questions in the room, I will ask some questions that were asked online. So Hadia Taleb asks, what does it mean, special events?
So it's a jargon. It's a name we give to the detection, the gravitational wave detection that we detect and we decide to publish before the catalogs, because we decide that is an event particular, that is not what we in jargon call vanilla BBH, so it has some peculiarities, and we don't want to wait for the catalog that usually is published with the data release to share with our colleagues that we have found this event. So it's a way to call it the event that we publish before the catalog.
So it's done for events that we thought are particularly interesting from astrophysics point of view, or for. Can you give an example maybe of a recent special event?
There were many recently. For example, the 231123 was the special event that was one of the massive we had, for example, but there were a couple that had special characteristics in terms of spin. There was one with the highest SNR that we released in this January, if I remember correctly. So it depends. So we decide, and depends what nature give us.
Okay, thank you. There is another question by Mehdi El Bouadouti, who asks, I probably missed this from the talk. Does the timeline tool give access to strain versus time?
No, the timelines, I don't think I can play with the laptop, right?
Oh, no, you can.
Okay, because I can show, I don't know if it's a wise thing to do, but I can, no, but yeah. But if I click here, there is directly the link. I don't know if, sorry, I'm not sure I'm doing
Ooh la la, live demo. Ooh.
A very bad idea, but okay. So if you go in O4A, for example, I don't know if I'm sharing the screen. Sharing the screen?
Yeah.
Okay. So for example, if you go in this page, you select a run, you will automatically see the start and the end of the run and the duration, so on. And then you see this nice link, which, as I say, this cat means category, and these are different kind of data quality category. But okay, if you select, for example, H1 data or L1 data, and you click on display, you will see the plotting. This was the plotting I was showing, but this is not associated with the strain. If you, for example, if you click here, what you see is it's small, but you see 3 columns. The first is the GPS start of a segment, of each segment. The second is the GPS stop. And the third is the duration. I don't know if I can zoom. I hope it's clear enough also for those that are in the room. So how we use it, we use this as input of a query. So you, for example, you download this table, is just a TXT file, and you download data from the GPS start to the GPS stop, looping in this list, for example.
Okay, thank you. Real quick, is there any question in the room here? No? Is it because the coffee break is soon? Right, okay.
Anyway, I'll be here for all the duration of the workshop, so you can ask me questions.
Okay, Well, thank you again, Agatha. We'll now stop the recording.